Scientific notation is a way for scientists to show really, really big numbers or really small numbers in an easier way to recognize. So, for example, if you wanted to know the number of atoms in a table, that's going to be on the scale of billions or trillions. And so once you get that many zeros after a number, it's hard for scientists to see exactly how big the number is. Same thing on the small scale. If you wanted to talk about the diameter of an atom, we're talking about nanometers, which is so tiny that you would have a lot of zeros. It would be like 0.000000001, and it's hard for scientists to read that. So one thing they can do is to write it into scientific notation. And the format is always going to be some number that falls between 1 and 9.9. So if it's less than 1 or greater than 9.9, then you're doing it wrong. Then it's going to be times 10 that's raised to an exponent. For example, 2.6 times 10 to the 23rd is written correctly in scientific notation. The exponent is going to tell you whether it's a really big number or a really small number. So if it's a positive exponent, if it's 10 raised to a positive number, it means the value of that entire number is greater than 1. If the value of the exponent is negative, it just means that the number is less than 1. So for each of these, to convert them into standard notation, for the first one we have 3.4 times 10 raised to the 5th power. So what you want to do is put your pencil on the decimal between the 3 and the 4, and you're going to move the decimal 5 places because it says 10 to the 5th. And then you have to ask yourself, is it a really big number or a really small number? And since the exponent on the 10 is positive, it means the value of the number is really big. And so to make it big, you're going to have to move the decimal to the right. If you moved it to the left, you'd be creating a number that's less than 1. So we know that couldn't be right. So you take the decimal, move it 5 places to the right, and then fill it in with zeros. So your answer would be 340000. Try the next 3 by yourself. And once you finish all 4 of them, check your answers and make sure you got the same thing that I did. Notice that for letter B, it's a number greater than 1 because the exponent is positive. For letter C and D, it's a really small number because they both have negative exponents. So in that case, I took the decimal and moved it to the left instead of to the right to make it a small number. Now let's go backwards. So if I give you a number, you should be able to put it into scientific notation. So what you want to do is first of all think about where the decimal is. And if you can't see the decimal, remember that it's at the right of the number. So right now the decimal for letter A is all the way to the right past that second 0. We need to move the decimal to get the value of the number between 1 and 9.9. So if we move it 1 place to the left, we now have 560, which is still too big. If we move it 2 places to the left, we have 56, which is still too big. If we move it between the 5 and the 6, we have 5.6, which falls perfectly between 1 and 9.9. So we're going to make it 5.6, then you're going to write times 10, and count how many times you move the decimal. Since you moved it 3 places, it's going to be times 10 to the 3rd power. And then just check to see if you need a positive or negative exponent. And since 5600 is a really big number, we want it to be a positive exponent. So your final answer is 5.6 times 10 raised to the 3rd power. Try the next 3 by yourself. And once you finish, check your answers to make sure that you got the same thing I did. Notice that for letter B, the exponent has a negative exponent, and that's because the value of that number is really small. It's less than 1. Whereas for letter C, the value is really big, and so it has a positive exponent. The last thing for this unit is just about graphing, because for chemistry we show data a lot of times using a graph because it's easier for scientists to see than just a list of numbers. And the most common type of graph that we're going to use for this class is going to be a line graph. Whenever you construct your graph, it's important that you have it labeled correctly. So make sure that you have a title on the top that shows you what the graph is showing. For example, in the picture on the slide, it says temperatures in New York City. That tells scientists what they're looking at. Don't forget to label both of your axes with not only a label but also a unit. So if you have some kind of numbers on the axes, you need to show what those numbers are showing you. For example, on the y-axis for this graph, it says degrees in Fahrenheit. The x-axis is always going to have your independent variable, and the y-axis will always have your dependent variable. And don't forget to scale them evenly and show those units. The last thing is just to be able to look at a graph and see if it's going to be a direct or indirect proportion, and it's going to be based on the slope of the line. So notice in that first graph, it's a positive slope, so as x increases, y also increases. And that shows a direct relationship between the two variables. The second graph shows an indirect proportion, where one variable increases as the other decreases. And that is all for this unit.